Good morning, everyone. Thanks for clicking this video. My name is Luna, and I am a research staff member in IBM Almaden Research. Today, I'll be talking about evaluating Intel 3D-Xpoint NVDIMM persistent memory in the context of a key-value store. This is a joint work with my colleagues in IBM and folks from Intel. In-memory key-value store has gained huge success and become de facto caching and storage solution in big data centers and the cloud. For example, we are all very familiar with Redis and memcached and the others listed here. In-memory key-value store cache data in DRAM at front end so that it can provide high throughput with millions of operations per sec, and also DRAM provides low latency with single-digit microseconds. However, volatile memory also has its drawbacks. First, the data are not persistent, so that it incurs overhead when it checkpoints data into the backend storage. Second, in a replication-based high availability setup, DRAM suffers from high data recovery time because once a node restarts after failure, it either needs to get the latest data copy from another node through the network, or it needs to read data back from the backend storage. Last, DRAM is expensive to expand the capacity when data scale. Fortunately, a new breed of storage class memory is defined and developed, among which Intel's 3D-Xpoint is the first in-breed storage class memory designed for the massive production. It is based on phase change memory technology and can be directly attached to memory bus. This product from Intel is called Intel Optane DC Persistent Modules, and I will refer it to Optane PM for convenience in the rest of the talk. Different from NVMe or PCM SSDs, Optane PM is byte addressable, and unlike volatile memory, it is durable. But the performance is slower than DRAM. Second, it has a big capacity with lower cost. Optane PM comes in with three capacities: 128, 256, and 512 gigabytes. Of course, the higher the density, the more expensive it costs. It is around $15 per gigabyte for the 128 gigabyte one, and $26 per gigabyte for the 256 gigabyte ones, as an example. However, the Optane persistent memory is still cheaper than DRAM, and we are expecting the price to fall as the market becomes more mature. With this new technology, it is natural to think whether we could replace the DRAM with persistent memory in in-memory key-value stores. Remember that persistent memory is durable, so we are able to solve the first two problems. First, data are naturally not volatile anymore, so we don't have the overhead to checkpoint data into the backend storage. Second, when the node restarts after failure, it doesn't need to reload data from the backend storage. Instead, it can perform minimal synchronization and immediately serve with data residing in persistent memory. Lastly, we can afford big capacity for large-scale data centers. These seem all good. However, bear in mind that persistent memory still comes with a performance disadvantage compared to DRAM. So the question is, can we still enjoy the benefits of high throughput and low latency, which are the reasons for in-memory key-value stores? As Optane is a newly released technology, there is still not sufficient research about the performance implications this new product will bring despite the new features, especially for in-memory key-value stores. So it is important to understand how persistent memory will affect the performance of in-memory key-value stores. To this end, Our paper presents a quantitative evaluation of Optane PM within the context of a memory key-value store. We first provide a thorough read and write performance evaluation with our micro benchmark to understand the raw performance of the media. Second, to fully extract the performance of persistent memory and utilize the features it provides, we design and implement a user-level in-persistent memory key-value store from scratch, called MCKVS, as an evaluation vehicle. We use MCKVS to evaluate the performance and scalability of a fully utilized in-persistent memory key-value store. Lastly, we compare the performance of using different media with MCKVS and also provide a comparison with different in-memory key-value stores to show the performance implications and the potential of adopting Optane PM in in-memory key-value stores. This is the agenda of my talk today. I have given an introduction and the background of our paper. Now I will talk about the raw performance of Intel Optane PM. Then I will give the performance results of MCKVS, including the comparisons I just mentioned. Finally, I will conclude with the summary of our findings. Optane PM can be operated in 3 modes: memory-only mode, app-direct mode, and mixed mode. In memory-only mode, persistent memory is exposed as a volatile main memory, and the DRAM is essentially an L4 cache in the hierarchy. Note that in this mode, data are not persistent. App-direct mode is exposed as a persistent memory that is explicitly managed from DRAM. Underneath, it can be either exposed as a file system called FS-DAX mode or a raw device called DAV-DAX mode. Mixed mode is simply partition the persistent memory with both volatile part and non-volatile part. In this paper, we configure persistent memory with app-direct mode as it gives the most freedom to manage both DRAM and persistent memory with the most capacity. This table shows our testbed specifications for the raw performance test. We have 12 persistent memory cards with 512 GB each, which makes it 6 TB in total. We configured the Optane PM with FS-DAX for the micro benchmark. We used our own benchmark tool called NVBench2, which is also open sourced together with our in-memory key-value store MCKVS. All tests are performed with a NUMA local setup, and we measure the throughput, latency, and the scalability. We didn't measure the performance of NUMA remote setup because we are mostly interested in the best case scenario as a baseline as our key-value store best performance target. This figure shows the results. Here the blue lines are DRAM and the green lines are Optane PM. Dotted lines are writes and the solid ones are reads. We can see that for both throughput and latency, persistent memory is up to 5.8 times slower than DRAM. Optane PM doesn't scale very well for the writes, but for low workloads, write latency is 2 times slower than the reads. This is because of the internal write buffer in the Optane PM device. Second, we also perform experiments with different data sizes from 32 bytes to 512 bytes. We can see that similarly, Optane PM suffers from scaling problems with increased concurrent accesses. We also see that larger data sizes show a better write performance when the smaller reads are faster. Lastly, We collect the latency latency c of each operation from the experiments and plot this histogram distribution graph. We can see that in Optane PM, we still experience the long tail latency. And in fact, it suffers from a longer tail latency compared with DRAM. Next, I will slightly introduce MCKVS, our customized in persistent memory key value store for performance, and the performance of using Optane PM in MCKVS. MCKVS stands for memory-centric key value store. It is a pure in persistent memory key value store designed from scratch to fully extract the performance of persistent memory. It is fully in persistent memory, so it doesn't use DRAM for any caching or any tiering. We configure the Optane persistent memory with DevDex mode to fully utilize the RDMA feature. And there's no page caching effect, no memory tiering, and we do not use PMDK high-level APIs due to the high transactional overhead. Instead, we adopted a simple crash consistency design. Please refer to our paper for more details about the internals of MCKVS if you are interested. To minimize the network overhead, we adopt RDMA for zero-copy memory access. MCKVS is the shared nothing architecture as the other popular NoSQL key-value databases. In order to compare with different media, we designed MCKVS with a pluggable backend, and it currently supports Optane PM, DRAM, and also NVMe SSD. And it's open source in GitHub, available for other researchers to experiment with. Now we present the evaluation results of adopting Optane PM in persistent memory key value store. We use the same test bed as previously mentioned, and additionally we equipped Mellanox Connect configured with Rocky version 2 as our RDMA setup. This graph shows the performance scaling of MCKVS. We can see that although Optane PM writes don't scale in the raw performance experiments, but we are able to scale the write throughput with number of threads within the context of key value store, because the key value store have the share nothing design, and we partition the Optane PM devices for each shard. The throughput scales up to 10 million IOPS for reads and 6 million IOPS for writes, which is very close to the raw performance. To further investigate the performance bottleneck of the reads here, we also recorded the overhead of the networks. Please refer to the paper for more detailed numbers. But as a conclusion, we found out that the read performance is bottlenecked by the network. Ideally, without the network bottleneck, we can further scale the reads instead of 10 million IOPS at 20 threads. But the write performance is limited by the Optane media. Next, we also plot the distribution of latency. Similarly, Optane PM-backed KV store shows a long tail latency as expected. In fact, the tail is longer than raw performance measurements. This is because the network introduced the additional latencies. However, still we can see 98% of the latency is within 10 microseconds for both reads and writes. Next, we compare the performance of MCKVS with different backend, namely DRAM and Optane PM. Here, we tested the DRAM with two implementations. One is called HStore DRAM. This is the same implementation we used for Optane PM. So it includes all the codes for handling cache line, flash, and the crash consistency. Another one, we use a simple map data structure in DRAM without crash consistency, and it is called map store. We can see that for both puts and gets, map store performs the best. This is expected as it doesn't have all the extra codes and overheads for handling crash consistency and the cache line flashing. Meanwhile, we also see that with the same implementation, DRAM outperforms Optane. This is also expectable. Interestingly, we found that the cost of crash consistency is up to 64%. Next, this graph shows the scalability compared to DRAM. Similarly, we see that all of the three scenarios scale very well with increasing threads. MapStore still outperformed the other two for the puts. However, interestingly, we see that as the workload increases, HStore DRAM starts to outperform MapStore. We think this is because the heap allocator for MapStore is shared across the threads. Meanwhile, in our MCKVS HStore implementation, we have one allocator for each shard thread because it's strictly share nothing, so that we expect low thread contention and a higher throughput than the internal map store. Finally, we compare MCKVS with Optane PM with other popular in-memory key-value stores, namely Redis and memcached. Note that both are DRAM, but they are not designed towards performance. For example, they don't adopt RDMA zero-copy memory features, and also they are not threaded. Here we use the YCSV benchmark with zipFan distribution and compared with both 50% read and 95% read workloads. We see that MCKVS with Optane PM outperform up to 10 times than Redis and memcached. Redis and memcached show a similar throughput for both workloads, while MCKVS show a better performance for 95% read workloads. This is because Optane PM media read performance is better than write performance. Meanwhile, the DRAM is sort of consistent between reads and writes. These results shows that adopting Optane persistent memory into KV store has a potential to be comparable or even faster than existing in-memory KV stores. But that requires very careful performance-oriented ad hoc design. Before I conclude, I want to say that we have more experiment results in the paper, including NVMe SSD results. Please check it out if you are interested. Finally, I will conclude today's talk with a summary of our findings. In this paper, we visited the performance of Optane PM and its implications for in-memory key-value stores. We found that Optane PM performs 2 to 3 times slower than DRAM, and in persistent memory key-value store can be up to 5.8 times slower than in DRAM key-value stores. We also find that writes on Optane PM don't scale with threads. Our experiment shows it scales up to 5 threads. And using Optane PM doesn't avoid the problems of long tail latency. We also find that the overhead of flashing cache line and crash consistency is more than 50%. However, our experiments prove that Optane PM shows a potential with careful adoption. It can offer in-memory key-value store with persistency as well as high performance. It can scale up to 10 million gets and 5 million ports operations per sec for single socket. Thank you for listening to my talk. Please visit our GitHub link for MCKVS and the benchmarking tools that are used in this paper. And also don't hesitate to contact me with any comments or questions. Thank you.